Yes, class. Am I audible to all of you? Mariam, Khadija, Sidra.
Yes, ma'am.
So Sidra was there in the last class. Khadija and Mariam,
Yes,
you
ma'am.
weren't there in this class. So I'll just quickly repeat it so that you're able to tally, because we have to start with torque. So a good thing is that we didn't start with torque properly. We were seeing the forces only. So what you have to remember is F is equal to QE. This you already know, that electric field is force per unit charge. So electric force would be charge into electric field. What you have to remember is if a positive charge is moving under the influence of electric field, the direction of force would be same as that of electric field for a positive charge. If the charge is negative, then this would be opposite direction. That's what you have to remember. This would be in opposite direction. All right, that's what we did. Suppose we had seen a question, 2 coulomb of charge was present. So F is equal to QE, 2 into 5. 5 is the electric field. We had 10 as the magnitude. So since this is a positive charge, force would also be directed in the same direction of electric field. So electric field was directed upwards. That's why for upwards, for y-axis, we have j cap. Similarly, an opposite question, when negative charge was made, minus j cap was get. Why minus j cap? Because this showed negative y-axis. This we had completed, and how the protons, particles, and electrons particle will move. How will you solve these types of questions? Separately on y-axis and separately on x-axis, write all the parameters. And when you have all the parameters present in front of you, then you can use the motions of equations of uniformly accelerated motions, like S is equal to ut plus half at square, to find out the time. So this is what we had completed. We didn't start with torque. Before starting with torque, you should have complete idea about this. Though when I was taking the bridge course of yours batch, I had repeated the vectors, cross product was also repeated, dot product. And in that class, I remember only Yahya was present. So it's a revision, quick revision, but I'll not be going into the details as I have repeated already in your bridge course. That time you people didn't attend. Only Yahya was present in the class when we were having the classes of vectors. So see, when you are having cross product, A cross B, it is equal to magnitude of A, magnitude of B sine theta, AB sine theta. And you have to remember this. See, just on the page, because torque is a vector quantity, so we'll be needing this. When you have this I cap, J cap, K cap, write it like this and start moving clockwise. So I cross J will give you whichever quantity is left. Like K cap is left, so it will give you K cap. So I cross J gives K cap. J cross K gives I cap. K cross I gives J cap. But when this order is reversed, J cross I, K cross J, I cross K, so these will give you all the quantities which are negative. The quantities will be negative. Now let's start with torque. So basically, what exactly is torque is the rotational analog of force. When we say rotational analog of force, we mean whatever function the normal force, the linear force is doing in the translation, the same action is being done by the torque in rotational component. Fine. This is what is meant by when you have the rotational component of force. So torque is it. Now, for torque to occur, there has to be an axis, and that axis would be separated at a point which is known as line of action. Line of action is what? Line of action is the point where the actual force will be occurring. Like look here. Look here. And since these two forces are acting in opposite direction, their magnitudes are equal, we say this is a couple. This was there in your class 11th also. In your laws of motion, you had this. So when one force is directed downwards, other force is directed upwards, both forces are separated by a distance, and both the forces have their own line of action, we say they form a couple, means two equal and opposite forces. This is not very important for your torque. Basically, we'll directly have the concept of torque. What exactly is torque? How do you calculate torque? So torque, you already know the 11th class torque which you have studied, that it is the perpendicular distance. You have the perpendicular distance R cross F. So when we say R cross F, you cannot change it and make it F cross R, because we are talking about vector quantities, and vector quantities, when you are talking about cross product, if you change their direction, if the direction is changed, the entire values will be different. So it's always R cross F. So perpendicular distance, and if perpendicular distance is not given to you, you will by yourself construct the perpendicular distance. You will drop a perpendicular and find your answer. But no one is going to ever directly see the separation and put it in the value. Fine. So perpendicular distance between the lines of actions into magnitude of force. That is what is our cross product. Now, one more thing before we begin this derivation. If you have electric dipole present, suppose I have a negative charge, this is a positive charge. So as per the last class, what we have studied that if positive charge is present, so the force is directed towards the positive charge, that is plus QE. And for negative charges, we have the direction opposite, that is this makes minus QE. So this is the force, and here this is the force. Plus QE you have, minus QE you have as the forces, right? Now, direction of dipole is also important. So direction of dipole from negative towards the positive we move. So dipole moment direction will be this, from negative towards the positive side. Now, here it is written net force on dipole, because when you are talking about torque, you are talking about the rotational component. And what about the linear component? What about the translational component? Will not the dipole move? It will start rotating. Yes, Mari, it will start rotating. But why will it not be moving forward? The question is, it will definitely start rotating because torque is active. There's a perpendicular distance, the forces are forming a couple, means one force is having this line of action, other forces having this line of action. Reason is that when we are calculating the net force, what is the force here? Plus QE. What is the force here? Minus QE. Why minus? Not because this sign is minus, we take the magnitude, because these are in opposite direction. So when you will subtract them, this will become 0. So your F net is 0. That's why the dipole is not moving forward like this. Otherwise, dipole would have moved forward also. That's why the dipole is not moving forward. Dipole is just rotating at its place. And again, I'm telling you, even if the dipole is made at an angle, at a random angle, let's say this angle. So see, this is a clear, elaborated diagram. Just understand properly. Minus Q is present, plus Q is present. They are separated by 2A. This is forming your dipole, plus Q. This is plus QE, minus Q. This is minus QE. These are the forces. Now, for calculation of torque, there was one condition required, which I had told you in the beginning itself. In the earlier part only, I had told you that the torque's radius which we take, it is always perpendicular. Now see, here we have taken a general case. Suppose this is making angle theta here. We still need a perpendicular. So Bn is the perpendicular that we have dropped. Understood? Bn is the perpendicular that we have dropped for our calculation. So see, P is what? Suppose P is the dipole. P is the, this question, this derivation comes. And whenever this derivation comes, you have to mention it from there. I'll tell you the electric field one. And E is the electric field. E is the electric field, P is the dipole moment. So we have to find out torque. Okay, now class, you answer perpendicular distance between them. These are the two lines of action. What is the perpendicular distance between these two charges? I have drawn everything on the board. You answer.
Ma'am, could you repeat the question?
Perpendicular distance between these two force charges. See, this is not perpendicular.
A and B?
Not A and B. See, A and B, this is not perpendicular. This is making angle theta. What is making angle 90 degree?
BN.
BN, correct. So you have one part as BN, right? Perpendicular distance. And can anyone tell the magnitude of force? That is very easy. Yes, class, magnitude of force. It's very easy. You know the charge, you know electric field. Force would be? Yes, class. What is the electric force?
QE.
QE, very good. This should have been answered by others also. QE. The force is QE. So we are familiar with QE, but BN, having BN as our answer, having BN in our formula, this is not a standard way to answer, right? So we still have to find out what is this BN. Now look, I have this triangle theta. In this triangle, we can do some manipulations, right? If in this triangle, I write sine theta, so sine theta will be equal to perpendicular upon the hypotenuse, right? This is the perpendicular and this is the hypotenuse. So opposite side is BN and hypotenuse is 2A, which is, rather I would write this first as AB. This is AB. So from here, I have BN equal to AB sine theta. And how can I write AB? AB can be written as 2A. See, separation between A point and B point is 2A. So this is 2A sine theta. Now let us put the value of Bn over here. So torque is equal to, look class, you have the entire derivation done. Almost the entire derivation is done. If we put it, this is 2A sine theta. This is Bn into Q. Now you have this with you. This is your final answer. But we'll try to just interchange the terms so as to make it a little bit familiar to us. If I interchange this is Q, this is 2A, this is E, this is sine theta. No difference. I can interchange the terms always. 2 into 3, I can write it as 3 into 2. Same thing. Can anyone now tell me what is this?
Dipole moment.
Dipole.
P. Very good. This is P. So you have torque as P E sine theta. See, isn't it similar to AB sine theta, which we have just seen? AB sine theta is A cross P. So torque ultimately is P cross product of dipole moment and electric field. All right, P cross E. This is what this is equal to, right? So now what torque will try to do? It will try to rotate the dipole in the direction of electric field. So that dipole, see, dipole is kept randomly in the electric field. Electric field is supposed like this. So torque will try to rotate the dipole so that this gets aligned with electric field. That is the task of the torque. It will try to align the electric field in this direction, like this. That's why this rotation is occurring. That's why we have this P cross E formula in our question. This is just the reason why we are having the formula P cross E in our calculations. So torque will try to align the, and torque will try to rotate the dipole and align it in the direction of electric field. Direction of torque dipole will rotate to a smaller angle. See, just understand. Same thing. Direction of torque is same. See, if suppose this was the torque present, if it rotates clockwise, this was the dipole, this is the electric field. Look at this example. This example first. Look at this example. Dipole is kept like this. So what will be the direction of torque? If the dipole will move like this, then it won't be a line. So what the dipole will do, torque will do, align the dipole like this. So what is this motion? Clockwise. So direction of torque will be clockwise. Clear? See, I'm repeating this. Dipole is like this. Look here. Electric field is like this. Now torque's work is to align the dipole in the direction of electric field. So see, if the torque will act anti-clockwise, it will be moving away, so it will never be realigned. Now torque will try to move clockwise and it will try to align it. So direction of torque will be clockwise. Suppose this is the direction and this is the electric field. So if it moves clockwise now, it will be moving away. So what dipole will do? Move torque anti-clockwise. So move the dipole anti-clockwise. So direction will be anti-clockwise. So this is how you determine. All right. Tell me, the entire torque's derivation is clear to all of you?
Yes, ma'am.
Yes, ma'am.
All right. See, whenever this question comes, this can come as a 5 marker also. And it comes as a 3 marker also. These are the 2 markers I have seen where torque is coming. One thing I'll tell you, whenever derivation of torque comes, start from this point. Electric field, electric dipole in uniform electric field. What will be the direction of electric dipole? Because you have to tell that translational equilibrium is existing. Net force is 0. That's why only you are focusing on torque. That's why you're not considering the forces, because net force is 0. So you'll have to mention this also. Start writing it or just quickly write the revision of cross product from here so that you have the torque part easier for you when we practice the questions. Start writing from, just make a note point. Just quickly write down this so that you at least have this. This is important.
Ma'am, can you scroll down?
Yes, Mariam, I'm scrolling up. Just a minute, class.
Ma'am, you can scroll down, I wrote.
R is the separation, the perpendicular separation from the axis of rotation. This is R, this statement.
Ma'am, can you scroll up for a second? I have to write the last sentence. Okay, ma'am, thank you.
Now I finished this part, you can scroll down.
This one only, no?
Yes, ma'am.
Look, in this question, you have an electric dipole which is placed in uniform electric field. This is shown in the figure. So you have to calculate the torque. So basically, what all things you have? Minus 2 millicoulomb plus 2 millicoulomb separated by a distance of 3 millimeters. This means that definitely this is making up a dipole moment. Now this angle is making 60 degree with the electric field, and electric field is 10 coulomb. So see, you know torque is equal to what? Torque is equal to P cross E. So this means that P, E sine theta you have. Now we do not have dipole moment. The first thing, electric field we have, but we do not have the dipole moment. So P is equal to charge multiplied by the separation between the charges. This is how we calculate. Charge multiplied to the separation between the charges. So what is the charge? 2 millicoulombs. We cannot use 2 millicoulombs. 2 millicoulombs has to be converted. 10 to the power minus 3. For milli, we multiply it with 10 to the power minus 3. So you have 2 into 10 to the power minus 3. This is the charge. What is the separation between them? The separation is 3 millimeters. So separation will be 3 into 10 to the power minus 3 meters. So this is 6 into 10 to the power minus 6 coulomb meter. This is the dipole. Now we have to substitute it in the formula of torque.
Ma'am, it's 2a, the distance.
2
The formula.
millimeters.
No, 2a.
2A is what? 2A is the
The
separation
form.
between the
Yes.
charge. And what it is given? 3 millimeters.
So won't it be 6 into 10 to the power minus 3?
6, the final answer. This or this, you're saying this has to be, you're saying this should be 6.
Yes,
Why?
because it's 2a.
So 2A, what is the definition of 2A that I've been telling you from the first class of dipole? What
It's the
is
distance
2A?
between.
Just write it as 2A. 2A is the separation between the charges. Clearly, I have mentioned this fact also in the class that we write it as 2A but never double it. Otherwise, your answer will be completely different. See, your answer will also double. See, if I was to write this answer, if I were to write, I would have written it as just A, just as L. But I have told you this fact that by convention, we have been following this as 2A. 2A is if A was the separation between both the charges and I would have written 2A, then we would have doubled it. Right now, 2A is the separation between the charges. What is the separation between the charges? 3 millimeters. So your 2A is equal to 3 millimeters itself. Q is equal to 2 millimeters. Like this. Is this concept clear to all of you? This concept of 2A.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
All right, be careful when you're solving the questions because this is something which is written by convention and that is a formula which you have to follow. If we were supposed to write through our variables, I would have never written this to make it confusing. But since this is by convention, you all also have to write it as 2A. Sometimes you will find it as 2L. But this 2 portion, 2 is there. A will be the half of the dipole. A is half of dipole. That's why 2A is the entire length of dipole. So we have dipole moment with us. So what would be torque? Dipole moment is 6 into 10 to the power minus 6. Electric field is given as 10. And we have sine 60 degrees. So this we'll write it as root 3 by 2. So we'll have this as 6 into 10 to the power minus 6 into 10 into root 3 divided by 2. This becomes 5. 5 into 6, this will become 30. So 3 root 3, 110, this becomes, no, this is 2, this is 5. 5 into 6 is 30. So this won't be 3. This would be 30 root 3. And what else is left? 10 to the power minus 6. So we can write this as 3 root 3 into 10 to the power minus 5. SI unit, Newton meter. See, radius into force. So Newton meter is the SI unit of torque. This is your complete answer. Write it down. If anyone is there who has not written the question, let me know. I'll scroll up. Otherwise, write it from here.
Done, ma'am.
All of you have completed. Anyone is writing, just text me done. If anyone has not written, just text me. Otherwise, I'll assume all.
Ma'am, can you explain this question again?
See, Mariam, in this question, you have electric field as 10 coulomb, 10 Newton per coulomb. Charge is 2 millicoulomb. What is the charge? 2 millicoulomb. So formula of torque is dipole moment multiplied to electric field. Electric field, you know already it is 10. But what about the dipole moment? So I have told you dipole moment's formula is take the charge and multiply it with the separation. What is the charge? 2 millicoulomb, right? See, milli. So 1 millicoulomb will be equal to 10 to the power minus 3 coulomb. So that's why we have multiplied this. So we have obtained 6 into 10 to the power minus 6. This is the dipole moment. So dipole moment, this multiplied to electric field is into sine 60. PE sine theta. We have derived this formula, no? PE sine theta. So P is this 6 into 10 to the power minus 6. Electric field E is 10 and this is sine 60. So when you solve, you will get this answer. Is it clear now?
Yes, ma'am, I understood. Thank you.
Okay. All of you have written?
Yes,
Anyone
ma'am.
writing?
Yes.
All of you have written. Let us start with the different cases which we have. Special cases just have the name as special cases. There is nothing as special or different. This you can always calculate. When the dipole is parallel to electric field. See, I'm just mentioning this separately because in the exams also this comes as a separate question. But see, nothing is difficult here. Special cases, this is just the name that is given. See, if dipole, suppose this is the dipole, this is kept parallel to electric field. What is the angle between dipole and electric field now, if they are kept parallel?
180.
0, 0, not 180. They are in the same direction. So 0 degree. Whenever two things are parallel, remember their angle will always be 0 degree. So torque is P E sine 0 degree. Directly torque will be 0. And we know already that net force was also 0, was already 0, that we knew. So it's a condition of stable equilibrium. What is stable equilibrium? See, stable equilibrium, let me tell you this, then I'll explain you what is stable equilibrium, what is unstable equilibrium. So this is a condition of stable equilibrium. If it is anti-parallel, this is electric field, this is the dipole moment. Now, Mariam, the angle would be 180 degrees because they are anti-parallel. Remember like this. So torque here is also PE sine 180 degree. Torque here is also 0. But we are saying this is a condition of unstable equilibrium. So what's the difference? In both the cases, we are getting net electric field, net torque as 0. Then why are we writing one as stable, one as unstable? Remember, if you think that original configuration can never be achieved on disturbance, I'll give you an example. Understand this example carefully for understanding equilibrium concept. Equilibrium, you know, when net force is 0. But there is a condition which we say stable equilibrium or unstable equilibrium. Suppose I have taken a bowl and in this I have taken a small ball. I have kept it here. So this is the mean neutral position of the ball. Now what I'm doing, I'm disturbing the ball. I'm disturbing the ball's mean position. Ball's initial resting position, I'm disturbing it. Suppose I am bringing and taking the ball and putting it here. When I will release it, class tell me, will the ball go to its original position or not?
Yes.
Yes, it would go, correct. This would go back. Or even if I keep it here, when I'll release it, from here also it will go. So see, it is again coming back to its original position. Here also the net force is 0. So this condition, this is called as stable equilibrium, where on disturbance, the original configuration of the body is achieved back. Like if you look in this case, if I disturb the dipole, suppose I bring the dipole here, still torque will have the tendency to align the dipole. So it will make it back to the parallel position. That's why I am saying this is a case of stable equilibrium. Why stable? Because the dipole on disturbance will reach to its original position. First tell me, the stable equilibrium part is clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am,
Now,
could you explain once again?
yeah, see, yeah. Whenever you have any configuration, this was just an example, this bowl and ball example. If you disturb the state, whatever is its resting state, and by nature, by the external forces, the body automatically comes to its original position because of presence of whatever forces. Now again it is coming back to its original position, it is staying. So we say that this is the case of stable equilibrium. Now why particularly this case is in stable equilibrium? Reason is that suppose this was the original position of dipole parallel to electric field. Ye thi na original position. Both were like this. Now I have disturbed it, right? I have disturbed the original position. What have we studied in torque? Torque has the tendency to align the dipole to electric field. Now what the torque will try to do? Torque will try to align this back. So again, I will have the original position of dipole. So I'm able to retrieve the original position of dipole. That's why now this equilibrium is called stable. Now is it clear?
Yes, ma'am.
Okay. Now class, look at one more example. Class will end 10:30, half an hour more. 10:30. 9 to 10:30. But not the next week, because next week some of you are having your exams like Zaina and all. After the next week, because next week you have to take your classes. After the next week, your class duration might increase, at least for completion of this electric field and this electric potential part. Okay, that we'll discuss later. Now pay attention. Suppose I have reversed it. I have inverted it. I have kept this bowl. I had the same bowl. I have just kept it like this. Now I have the ball kept here. Fine. This is an equilibrium. The net force here is also 0. See, F net is 0 also here. Now what am I doing? To check the stable or unstable equilibrium, I am changing the position. So what I'm doing, I'm producing a slight disturbance, slight force through this ball. So it will move down. Class, tell me, will it come back to its original position?
No, ma'am.
No, no, ma'am.
Time it won't come. Correct. Even if I move it here, it won't come to its original position. Here also on the ground also the ball is in equilibrium. No force is acting, it is not moving. But this is unstable equilibrium. Why? Because original configuration has been disturbed. So this is the unstable equilibrium. Like if when you will come to this dipoles example, look here. Here what is happening? Electric field and dipole moment both are anti-parallel to each other. Both are at an angle of 180 degree to each other. Now torque, it is difficult for the torque to act at so many angles and align it, because this is completely far apart from each other. So this will always stay in this position. Though equilibrium is there, but this is the case of unstable equilibrium. If the angle was less like this, so it would have gone. But now the torque cannot align it back because they are completely anti-parallel. That's why I am saying these are the cases of stable and unstable equilibrium, which you have to remember. Last case is very easy. See, if I give you one example also here. If I have this flat surface and I am keeping the ball here is also in neutral. I am keeping the ball here, it is still in neutral position. So basically the position is only changing, nothing else is occurring. Third case is if dipole is kept perpendicular to electric field. Now what is happening? Torque is equal to PE sine 90 degree. Sine 90, you know it is 1. So torque will be just PE. Means this would be the maximum value. This is the maximum value of the torque possible, right? Because sine
So,
90,
ma'am, there will be no rotation in this case.
there won't be any rotation in this case because it is perpendicular. Torque will try to align it, but see, since this is the maximum torque which is occurring from both the sides, clockwise and anti-clockwise, it is difficult that dipole will come to electric field. but torque will try to overcome it. It depends now on the magnitude, whether the magnitude of dipole is so strong, electric field is so strong, but we will get a good amount of torque here because the angle is 90 degrees. This is the maximum value which is possible. So this is a case of neutral, but this is not equilibrium. This is not, the equilibrium has not been achieved over here. This is what is the case. Clear till here?
Yes, ma'am.
Just write till here.
Ma'am, I want to know in exam, how will they ask questions on these special cases?
See, special cases will not be given as directly to write all these. They will be using the concept. Dipole is kept parallel to electric field and so this is happening. And then find out the net torque, find out the equilibrium, mention which type of equilibrium is existing. Or sometimes it can happen that you can get a question to give an example of a condition of stable equilibrium, because equilibrium is there in your syllabus of electric charges and fields. So from there, you have to explain the case. Otherwise, these terms will be mentioned in the question. And I think at the corner or somewhere, draw this also so that you remember what we looked at.
Done. Done.
See, you had SHM in your class 11, where you had seen simple harmonics condition. So, a question comes in your electric charges and field, which is related to your torque, where you have to show the charges are executing SHM. For that, just a quick revision for that. Angular SHM we had seen. When you have the linear SHM, so we have the condition that F is equal to minus Kx. But when we're talking about the angular SHM, we write the condition as torque is equal to minus K theta. Torque is the restoring torque, K is the constant, theta is the angular displacement. And minus sign is just showing that the pendulum or the bob, whatever is the body, is returning to its mean position. Direction of the restoring force or the restoring torque is always towards the mean position. That is the condition. And oscillation should be executed. And apart from this, we had seen some other conditions also, that angular frequency was written as under root K by I. I was the moment of inertia. Otherwise, we used to write under root K by M. M was mass. But here in angular, we are considering the angular portion. So we will be writing it as under root K by I. Now, T is equal to 2 pi divided by omega, and omega is equal to 2 pi by T. So these are from your class 11th portion. So this you must be knowing it already. And you have a question here. See, these are the types of questions which which I was mentioning, that electric dipole is placed in a uniform electric field. And you have to show that its motion is executing SHM. And you have to calculate the time period also. So see, electric dipole, if it is executing SHM, how will we show? Firstly, we'll have this electric field with us. Fine. Electric field will be present, and then you will be having the dipole. So suppose the dipole is here, and now I have disturbed the position of the dipole. So on disturbing, suppose this is the position of dipole. So torque will try to align the dipole to its original position. Let's even say this angle that is formed here. This is theta. This is now whatever the torque is performing angular motion, we have to find out its time period. So firstly, you should know that the restoring torque is acting. Restoring torque is acting. So torque, we have calculated it as minus PE sine theta, right? Now, there is small, all these things you've studied in your class 11. We have done it in class 11. There is one small angle approximation. Small angle approximation basically says when the angle is very small means less than 15 degrees. If the angle is this much small, then you can say your tan theta or sine theta are almost approximately equal to theta. Sine theta is approximately equal to theta. So you can replace this sine theta because see here when the dipole is moving, a very small angle is being produced. So we say that this torque is equal to minus PE theta. Can you see this is similar to torque is equal to minus K theta. This is the angular displacement which is coming. This is the angular see theta is the angular displacement. Means how much angle has been shifted. So this is angular displacement which is coming. So this is the condition of SHM. So if SHM's condition, we have achieved SHM's condition, you know torque is directly proportional to theta. So what is the K here? K is equal to PE over here. And we require K. So firstly, this is clear that the system exhibits SHM. See, system exhibits SHM. This is clear because of the fact above torque is equal to minus K, theta is being achieved. So this is clear. Now, omega is equal to under root K by I. What is K? Omega will be equal to PE divided by I. What is time period equal to? Time period is equal to 2 pi by omega. So time period will be equal to 2 pi. What is omega? Under root PE by I. So under root PE by I, this is the time period and that was the test. This only you had to calculate. Write it quickly from here. Make a note point first. This is from your class 11. Others also write just done in the chat column once written. All right, class, that completes with the torque portion. Just one question I